IGCSE Physics paper for summer 2016, and this is paper 41. Let's jump straight in. All right, a bus travels at a constant speed. It stops for a short time and then travels at a higher constant speed. Using the axes, basically, we just need to draw the distance time journey for the bus. So what we know is it's at a constant speed, so it's a straight line, okay? And we're going to just assume that it's positive. It's moving away from some destination. It then stops, so it stays at the same distance over some time, so it's flat again. And then it moves at a higher constant speed, so it's another straight line with a higher gradient. And we can see that's what I've drawn in here. I mean, it's not well drawn, but yeah, straight line. And we notice that the gradient of this one and this one's different. Flat when it stops, and then higher gradient. All right. A elevator starts from rest at the ground floor of a building. And basically you need to, you get given this, this figure here. And then it asks you to calculate the distance traveled while doing all of this. And basically we know that it's the area underneath this curve here. So what we have to do is essentially we can either calculate the area of this triangle, this square, and this triangle over here, or we can just use a trapezium. And you just get the area and you stick it in, and that's your answer. All right. Okay, figure 2 shows a dummy of mass of 70 kilograms used in a crash test to investigate the safety of a new car. The car approaches the solid barrier at 20 meters per second. Let's always underline our important bits of data. It crashes into the barrier and stops suddenly. Calculate the momentum of the dummy immediately before the crash. Okay, so it's just the mass times by the velocity. So we've got the mass, we've got the velocity, and we can calculate the momentum. The units are either Newton seconds or kilograms per meter seconds. Kilograms per meter second, sorry. Determine the impulse that must be applied to the dummy to bring it to rest. Well, basically, the impulse is essentially the same as the answer above. The velocity then is therefore 0, so it goes with this momentum to 0. In the crash, the passenger compartment comes to rest in 0.2 seconds. Calculate the deceleration of the passenger. Okay, so we know it goes from 20 to 0 in 0.2 seconds. So we just say 20, well, minus 0 if you want to put that in there, all divided by 0.2, and we get about 100 per meter second squared. Okay, the seatbelt and airbag brings the dummy to rest so that it does not hit the windscreen. The dummy has an average deceleration of 80 meters per second. Calculate the average resultant force applied to the dummy of 70 kilograms. Okay, so we just know that force is equal to mass times acceleration. We know the force and we know the so we know the mass and we know the acceleration, so we can calculate the force. Nice and simple. The deceleration of the dummy is less than the deceleration of the passenger compartment. Explain why this is a benefit for the safety of the passenger. Well, basically, if the deceleration is less, then the overall force is less. And we're trying to minimize that force because it's that force in the human body that does the damage. Okay, figure 31 shows an oil tank that has a rectangular base and dimensions, blah, 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 blah. Just always remember, underline them so they pop out when you need to draw out that information. So calculate the pressure exerted by the oil tank on the oil on the base of the tank. So it's just density. Well, I remember it as rho GH, but it's basically density times by the gravitational constant times by height is what we call the hydrostatic pressure. And that is just quite simply calculated as 850 that's the density multiplied by the gravitational constant, which we can assume is 10, multiplied by the height, which is 1.5 meters. Boom. Now it asks you to calculate the force exerted by the oil on the base of the tank. So it's just the pressure times by the area of the base. That's the answer there. Okay, so then it says calculate the force calculated in that part of the question is the weight of the oil. Calculate the mass of the oil in the tank. And we can go about this two ways. They sort of hint to basically take the force and divide it by the acceleration. It's one way of doing it, or we can take the volume and multiply it by the density, and then we can get the mass up the side. Just plug those numbers in and you should get the mass. When he is checking the level of the oil tank, a man drops a brass key into the oil, and it sinks to the bottom of the oil. State what this shows about the density of the brass. Well, the density of the brass is higher than that of the oil because the buoyancy force is not enough to hold it up. All right, explain how attaching the key to a piece of wood can prevent the key from sinking. So essentially what you're doing is the combined density of the wood and the oil is then less than that. Sorry, the combined density of the wood and the brass is then less than that of the oil. Explain in terms of molecules why it is possible to compress a gas but not the liquid. Essentially, it's got to do with the space between the molecules. So in the case of a gas, there's lots of space in which to compress, but for a liquid, there is very little space, and so you cannot compress it. Two containers made of insulating material contain the same amount of water at room temperature. The containers do not have lids. The volume of the liquid in each container gradually decreases. After a certain time, the temperature of the water has decreased to below room temperature. Explain in terms of the molecules why the temperature has decreased. Well, essentially, it's a result of evaporation, and you need to then also explain what evaporation is. And essentially, the fast-moving molecules. So, in a liquid or a gas, you have sort of a distribution of fast and slow moving molecules. And when you have like a free surface, you've got fast moving molecules, and the fast moving molecules at the free surface, as opposed to slow moving molecules at the free surface, will escape. The fast ones escape, taking away energy, and then the energy of the entire system decreases. One of the containers is wide and shallow, the other container is narrow and deep. Predict which container has the greater cooling. Explain your answer. So the wider, shallower container is going to have greater cooling. And this is essentially because the surface area is higher, and that means that more fast-moving molecules can escape over the bigger surface area, and it'll cool quicker and also increase the evaporation. So you have something called evaporative cooling. All right. State what happens to the molecules of the gas in a sealed container when the temperature of the gas is increased. Basically, if you increase the temperature, you increase the speed of the molecules and other things like the collisions and so on, but we can get into that in the next part. A quantity of gas is contained in a sealed container of fixed volume. The temperature of the gas is increased. State in terms of molecules 2 reasons why the pressure of the gas increases. So basically, the molecules, because of their increased temperature, have increased energy and kinetic energy of the individual molecules. So they move around a lot more, and they hit the sidewalls of the container more, so they impart more momentum by having more collisions with the sidewalls, and they also hit the sidewalls with more momentum per molecule. So you transfer then more momentum to the sidewalls, and that's also increases pressure. Okay. A helium-filled balloon is held at ground level. The volume of the balloon is blah blah blah. The pressure of the balloon is this amount. The balloon is released and rises to a height where the volume becomes this much. Calculate the new pressure of the helium. Assume that the temperature stays constant. So whenever you see temperature stays constant, you can use PV equals a constant. So you basically just chuck in these different values that you've taken from there, and you should come out with that answer. Quite a straightforward question. suggests why it may be necessary to release helium from the balloon as it rises even higher. Basically, what's going to happen is the balloon's going to just keep increasing in volume, so eventually it might burst. So you just would want to release some of that so the pressure drops and you can sort of regulate the volume of the balloon. Okay, 2 students are measuring the speed of sound. Students are provided with a starting pistol, a stopwatch, and a long measuring tape. The starting pistol, when fired, produces a loud sound and a puff of smoke. So we have the actual sound wave, and we have a visual cue, the puff of smoke. Same time. Describe how the students use the apparatus and how they can calculate the speed of sound. So essentially, we're going to assume that compared to the speed of sound, speed of light is nearly infinite. So basically, they see the puff of smoke, and then there's a delay, and then they hear the sound. So what they do is they measure out a set distance, make it nice and long. That means that they can reduce their error, because you don't want to be standing right next to the pistol because you'll just hear the sound instantly. You won't be able to distinguish. So what you'll do is you'll wait for the puff. You'll see the puff of smoke, and as you see the puff of smoke, you'll start the stopwatch, and then you'll wait until you hear the sound. And the instant you hear the sound, stop the stopwatch, and now you know the distance between the two, and you assume that the speed of light is pretty much infinite compared to the speed of sound, and you can then use the time and the distance to calculate the velocity. Okay, a device at the bottom of the sea emits a sound wave of that frequency. The speed of sound in the water is this much. Calculate the wavelength. You just chuck it into your formula, which is the velocity is equal to frequency times the wavelength, and you just divide the velocity by the frequency, and you get the wavelength. It should be in meters. Sound wave passes from the seawater into the air. State what happens, if anything, to the frequency of the sound, the speed of the sound. The frequency doesn't change. The reason why the frequency doesn't change is if we look at a point and it's bobbing up and down, right? Okay, so the sound, and let's say this is the surface of the water, and we have sound propagating from here. This point's going to bob upwards and downwards. And this point is sort of the same. Let's imagine it sits right at the boundary of the air. Oopsie, the air and the water. Right? Because it sits at the boundary between the air and the water, this point essentially has to move with both. In order for it to move with both, what we can see is that it has to move at the same rate. So the frequency, which is the inverse of the rate, if you want to look at it that way, has to be the same when a wave transfers from like one medium to the other. However, the speed of and then when we look at the speed of sound, well, we know the speed of sound is slower in air. So that sort of explanation is more to remember why that is the case, but you can quite simply say that the frequency just does not change. It's the wavelength that changes, and the speed if the speed of sound changes when looking at this equation. Okay, a ray of light passes through a length of curved optical pipe. Draw a diagram showing the fiber and the path of a ray of light. So I've just done a pretty crude drawing. Basically, it sort of internally reflects, so it bounces off the end walls. Describe one use of the optical fibers in medicine. You may draw a diagram. There's a whole range of different applications. So it can be used to sort of burn cancer cells. It can be used as sort of like an endoscope, because the light sort of passes down it. So you can sort of like, instead of having a bulb at the end of a pipe or a camera at the end of a pipe, you can just use the optical properties to send light in and out of the human body and so on. This is quite straightforward, just like draw lines to the associated speeds. You're just going to have to remember that. Then the refractive index of a block of glass is 1.5. Use the value of the speed from light from B to calculate the speed in this block. So you just know that the refractive index is the speed in air over the speed in glass. You just rearrange it, and you should get about 2 times 10 to the 8. All right, 2 straight vertical wires, X and Y, pass through holes in a horizontal card. Figure 8.1 shows the card viewed from above, and so we know we can use the right-hand rules for the magnetic field. So we can see that it's rotating like this. And now it's asking, there is a current in each wire in the downward direction. So then you basically just need to draw ticks. Place ticks in each blank column of the table to indicate the direction of the magnetic field and the direction of the force. Okay, so if we start looking at this, we say the magnetic field at Y. Okay, we can see it's sort of rotating around. So this, I've actually drawn the interaction, the combined magnetic field. But if we look at the magnetic field of X on Y, it's actually also just sort of round and down. Okay, so it's towards the bottom of the page, tick. Now the force at Y, the interactions are going to push, so it's going to be, it's going to pull, so it's going to be the forces to the left. All right, state and explain whether there is also a force, on the wire at X, and the answer is yes, because Y is producing a field on X, and basically yes, because of the resultant field. All right. Figure 8.2 shows a DC supply connected to the input transformer. Basically, just, the question then says, when the switch S is closed, the needle of the galvanometer deflects briefly, then returns to 0. Okay, so because this is a DC supply, what's initially going to happen is going to be initial buildup of the magnetic field. And this sort of transient buildup, as it sort of builds up, is going to cause a resultant magnetic field on the other side. And this build-up process, this sort of change in magnetic field, induces a flow of current in the opposing wire. However, once the field is built up to its level, and that sort of depends on the amount of current supplied, this will eventually just reach a constant. So there will be no change in magnetic field. And so this will then just sort of fall back to 0. You're looking at the key word that we use in science as a whole is the transient process. But once it sort of goes from one state to the other state and stays at that state, and everything is constant, and it won't, there will be no transients to drive. There will be no moving magnetic field, if you want to look at it that way. All right, this is quite a straightforward question. You just need to apply either series or parallel resistance equations to work out the overall resistance step by step. So if we're looking at resistors A and B, we see that they're just in series, so we add it up. So if we look at resistors A, B, and C, so we just use the previous answer for this one's total, and then we use that in parallel this time with the other two. We can then work out the answer. And then we use this whole combined thing in series again with D to work out the overall resistance. All right, calculate the current in the battery. All right, so if we're calculating the current in the battery, we basically just want to use V equals IR, and we just need to use the total resistance now, and we can just work out the answer. The energy transfer from the battery to the circuit in 50 seconds. So basically, we start off with calculating the power. So we know the voltage, we know the current from the previous calculations. Basically, we times that to get the power, and we times the power by the time to get the total energy transferred. Okay, you just need to know your symbols. This is an LED. In the space below, draw the symbol for a NOT gate. Okay, it's just this sort of triangle, and the NOT part is usually the sort of denominated by this little circular thing. Okay, number B shows a digital circuit. All right, so we've got an and we've got an or. They just want you to complete the table. So for an AND, basically you need to have both 1 and 1s to get a 1, because it's in a sense one input times by the other input. So we know if you have a 0 cropping up in any of these two columns, this will automatically be 0, and we have to wait until we have 2 1s in order to have a 1. So you can see that there are 2 1s here. All right, now the results of this is then passed into this combined with D, and then we need to work out what happens at E. And this is essentially a plussing mechanism. So in OR is you basically need you just need either 1 to be 1 for the output to be 1. And if both are 1, then it's also 1. So it's not quite the same as a plus, but it's down those lines. It's a nice way of remember it. So we just go through, and every time we have at least 1 on one side, we can chuck a 1 in. If we have 0s, then it chucks to 0. But here we've got 1s, we've got 1s, we've got 1s, so it's all 1s there. So you can just complete the table. Okay, then they basically give you this table, and they ask you, okay, in order to get this sort of output, what do you need to change in this sort of circuit here? And so you basically want to, if we look at this table and we compare, the only time that it's 1 is when both the inputs are 1 here, right? So both of these are 1, and we notice that okay, that only happens in this case, and so in these cases we have to get rid of the 1s and stick them to 0. And that happens if basically we get rid of this property of this needing either A or C. In this case, I'm going to put it that way, A or C being 1 or 0. So basically we need to just replace it with an AND gate. So basically both have to be 0. So we just replace the OR with an AND. All right, then it goes on to, so then we move on to radioactivity questions. So it states bismuth 214 has this half-life. The nucleotide notation is this. State the composition of the nucleus of bismuth, blah, blah, blah. Okay, so we just use the information from here. So we know that 83 is the number of protons. We know that the top number is the combination of protons and neutrons. So we just take the top number and we minus the bottom number to get the number of neutrons. So we have 83, number of protons. 214 minus 83 is 131, and those are the number of neutrons. Sorry, that's not, I should maybe put more here, neutrons, and not newtons. Okay, bismuth decays by beta decay to an isotope of polonium. Complete the equation. And basically we know that if we have a beta decay, the number of neutrons and protons doesn't change. But what happens in beta decay is that a neutron ejects something similar to an electron, well, it actually is an electron, and turns into a proton. So we know the number of protons increases, and so we know that the result here is the amount of neutrons and protons don't increase, but the amount of neutrons on their own, protons on their own increases by 1. Okay, the count rate from a sample of bismuth is 360 counts per second. Predict the count rate from the sample after 60 minutes. So we have to go all the way back here. So we know the half-life is 20 minutes. So we can see that if we go 60 divided by 20, we can see that it goes through 3 halvings. So you just start off with 1. So you say 360 divided by 2 for one of the halvings. Gives you 180. Say 180 divided by 2. Gives you another halving, is 90. And then you say, 90 divided by 2. Gives you the last halving. And so the count rate drops to 45. And it says, state 2 of the social/economic or environmental issues involved in the storage of radioactive materials with very long half-lives. And you can list a range of complexities. It's actually quite expensive too because of the danger associated with it. If it's badly stored, it can be released into the environment, into like water supplies, and then can cause absolute havoc in terms of health issues. But this is if it's badly stored. It'll always be quite expensive to store, but it could be stored in quite safe ways. But there are a lot of hurdles to overcome this. Anyway, thanks guys. Hope that was helpful, and we'll see you soon.